Good morning, good afternoon, and good evening, everybody. Welcome to Network Considerations for Multicast in AV. Today's presentation on multicasting is going to be presented by a couple applications engineers here from Biamp Tech Support. We've got myself, David Berkey, and my colleague, Frank Pajak. So please feel free to ask any questions during the session. I think we're going to kind of get through the presentation here, and then we'll work towards answering a few of those towards the end of the webinar. Also, a copy of the slides and a recording will be emailed out within about 1 to 2 days following the webinar. So our goal today is to talk about AV networks and multicasting. Okay, AV networks can scale up quickly. They can require some pre-work to create a positive impact. And we hope today to cover some of the concepts related to multicast and provide some tools as well as a reference that might help the next time you find yourself dealing with troubleshooting multicast. So, let's start in the beginning, right? Networks were simple. All hosts or endpoints were connected to a single broadcast domain, and really everyone could talk to everyone. And while layer 2 broadcasts could reach hosts in a subnet, this didn't necessarily scale too well, right? Too much broadcast traffic could oversaturate the network. But the problem is that this is kind of where AV traditionally lived, out on the edge. So in the good old days, you could throw in any unmanaged switch there and it would work. And think back to using something like CobraNet. So how do we get here to the world of Dante, AVB, AV over IP, and sort of what happened to that single broadcast domain we used to live in? Well, in order to better manage some of the problems created by having just a single broadcast domain and have a little bit more control over the chaos, networks began to use some tools. Right, so the first tool we began to use were VLANs, which asked the question, how can I bound my network traffic to prevent it from going out to other parts of the network entirely? You might have a control infrastructure or web server, and you don't want that server to be inundated with unnecessary traffic. You could build physically separated networks, which are costly, complicated, and time-consuming, or you could create virtual LANs or VLANs. And what that means is, creating a logical grouping of network nodes on the same physical network. And it allows us to create a little separate subnetworks that are comprised of different types of devices. But with the solution of VLANs, allowing me to partition things and distribute the load, there came some other challenges, right? So, one of these is VLAN configuration. You have to manually configure VLANs. So there's the potential you can configure the wrong VLAN since it requires manual setup. This requires manual overhead. And as a result, whenever you open the door for human interaction, you've got Mr. Murphy standing there with Murphy's Law, and therein exists a potential of goofing something up. Also, too, what happens even after you've configured something in the correct VLAN and someone comes in behind you and unplugs something and plugs it back into the wrong port, possibly on a completely different VLAN. If that port is assigned to a different VLAN, you might have moved a video stream to a corporate network port. So now you're sending all that data somewhere it shouldn't even go. And subsequently, you've ruined your video stream. One other VLAN woe is that if the switch breaks, you got to have great documentation trail to know how to configure that VLAN to get it all working again. But ultimately, overall, at this point, VLANs are pretty well understood. But they did create another problem that we might still need to share unicast or broadcast traffic between these logically separated networks. So, that kind of leads us to routers. And routers can be used to forward packets between VLANs, allowing devices on these logically separated networks to still communicate with one another when needed. Right, so we can use these routers to get VLANs talking together again, and Unicast is going to know where traffic is going, being point to point, but we still need a router to get between VLANs, in some cases using inter-VLAN routing. But the problem now is how can we get that layer 2 broadcast traffic back to layer 2 after hitting a router, and how can we do this in the most efficient way possible? So begins the quest for a solution. And this ushers in what we know today is a layer 3 broadcast overlay solution using the concept of IP multicasting. So this goes way back to Steve Deering, 1985-89 at Stanford University. I developed a layer 3 overlay broadcast domain solution that provides support for communications channels that were potentially broken with the introduction of VLANs and routers. Traditional IP communication allowed a host to send packets to a single host via unicast transmission, or to all hosts on the network via broadcast transmission. But IP multicast comes in and provides this third possibility, allowing a host to send packets to a subset of all hosts as a group transmission. Ultimately, IP multicast is a bandwidth conserving technology that reduces traffic while simultaneously delivering a single stream of information to multiple recipients. So let's take a quick look at the differences between unicast and multicast, right? So when you make a telephone call, you enter a certain number to be able to speak to a person. A flow of information between just you and that other person. This is unicast. When using unicast on a network, the packets are resent to the network each time a new destination is added. So if you have 5 devices on the network who want to receive that data, the source needs to send out 5 separate unicast transmissions. Well, this may not be an issue depending on the size of the data traveling through your network or the number of receiving devices. I mean, it's certainly not an efficient transmission method. So IP multicast comes in and enables information to be sent from one node to multiple recipients. This results in a single packet sent to all destinations that want to receive, which saves bandwidth and network overhead, right? Multicast applications come in a couple different flavors as well. So you have one-to-many. You think about broadcast concerts, TV, stock tickers, just general announcements. You might have many-to-many multicast where you have an AV conference, whiteboards, online collaboration, or online video gaming. Or you might have many-to-one, which could be like a video surveillance system or some level of online polling. Now, no matter which form of communication you're using, if you want to reach a specific contact, you need to know how to address them. And this is obviously no different with network technology, which uses IP and MAC addresses to identify the intended recipient. And looking at the table shown here, it defines the different address classes currently in use. Class D is notably reserved for the purpose of multicast groups. Now, multicast is not simply a collection of just individual unicasts. What they are instead are messages that are sent to these special Class D multicast addresses or groupings the receiving devices indicate they want to listen to. This results in a redirection via a router to all members of the multicast group. And the multicast group refers to a specific set of network devices that have actually requested to receive that specific multicast transmission. The key here is that multicast IP addresses, they're different than other IP addresses in that they're not associated with a single device, but they're rather a destination-only address, which identifies a group of devices. So let's take a closer look at these address groupings, right? So the Class D IP multicast range is from 224.0.0.0 to 239.255, 255, 255. And this is further divided into 3 multicast address groups. It's local, globally, and administratively scoped addresses. Now, the locally scoped addresses, they're reserved by the Internet Assigned Numbers Authority, or IANA, for network protocol use. These all kind of fall in the address range of 224.0.0.0 through 224.0.0.255. Multicasts in this range are never forwarded off the local network, regardless of their time to live. This is, as a result, this is usually set as 1. The table we're showing here highlights that many Biamp and in this case even Audinate multicast addresses are leveraging this addressable range for device communications. Some common examples of other network protocols that kind of sit in this range are OSPF, EIGRP, RIP, version 2, VRRP, and PIM, which is actually a multicast protocol specific to routers. An important note here is that most multicast applications operating in this link local address scope, including these routing protocols, do not subscribe into their multicast groups via IGMP, which we'll get into here in a moment. The reason being is that it's not technically necessary to do so because all of these link local multicasts are actually never forwarded beyond a router. Now we have globally scoped addresses. These fall in the range of 224.0.1.0 through 238.255, 255, 255. And looking at this table, we see a familiar protocol that falls in this range. If you look at 224.0.1.129, this is utilized for the Precision Time Protocol, or PTP, which is used to synchronize clocks on a network. We might come across this as the protocol used for clocking in Dante communications. Then we have administratively scoped addresses. These are 239.0.0.0 through 239.255, 255, 255. And these are reserved for use inside private domains. These are similar to private IP address space that is used within boundaries of a single organization. These limited or administratively scoped addresses are constrained to a local group or organization. We'll see an example of these addresses later in the presentation when we take a deeper look at a Dante multicast flow.
Yeah, so now the plot actually thickens here because once you have your multicast IP addressing, this is when you can develop your multicast MAC addressing, right? So all of this asks the question of how does a router or switch relate to a multicast IP address with a MAC address, right? So normally network interface cards on a local area network segment will only receive packets destined for their burnt-in MAC addresses. However, this is an issue because there exists no address resolution protocol equivalent for multicast address mapping. In this case, we can use layer 2 multicast MAC addressing, but unlike physical MAC addresses that are burnt in and hard-coded to the network interface, multicast MAC addresses are actually derived from their multicast IP addresses using multicast group names. We then derive our multicast MAC addressing knowing that all multicast MAC addresses will begin starting with 01005E. This is the organizationally unique identifier, and this OUI information actually is owned and furnished by IANA, the Internet Assigned Numbers Authority. So the wildcard in this comes in that the remaining 6 digits used get built using only part of the multicast address that is used. This runs into an issue that historically happened during the RFC process where we lost 5 bits of information. The multicast address range actually has a fixed 4-bit header, right? So it's binary 1110, and this leaves 28 bits of significant IPv4 addressing to work from. So mapping this to layer 2 MAC addresses leaves us in a situation where we don't have enough bits. And the story goes way back to Dr. Deering again, who during the RFC process knew that to make multicast work, he would need to exclusively own the block of layer 2 MAC addresses. Owning this block would give him 24 bits of unique information exclusively. And to accomplish this, Dr. Deering would need to purchase the complete address space from IANA, allowing Dr. Deering to map all of his IPv4 multicast with unique addresses to layer 2 that require the 16 OUI. So Dr. Deering asked Stanford for some additional funding at this point to purchase those 16 OUI, and in 1985 money, this was going to be pretty expensive. They were about $1,000 per OUI, which came out to about 16,000 bucks. And because sometimes doctoral theses go nowhere, Stanford decided to purchase only 1 OUI. And in their genius, Stanford gave Dr. Deering only about half of the space and kept the other half for somebody else that may need those MAC addresses for future studies. So as a result, we ended up with 23 bits of significant information usable to map IPv4 layer 3 addresses down into layer 2. And that means we get a 32-to-1 IP address to multicast MAC address mapping. And this issue comes up now that we have a problem, right? You have 32 multicast IP addresses with the same multicast MAC address out on your network. So this means you need to be extremely careful not to create overlaps using only known local or existing multicast broadcast addresses when working in IP multicast environments. So now that we've discussed the concept of IP multicast groups, this comes the question of how does a router or switch know which ports does it want to join these groups to and receive multicast traffic with? Well, the answer here is IGMP, Internet Group Management Protocol. And this is really just a set of control messages that IP multicast enables devices send to each other to join and leave multicast groups. So we can look at this thinking in this example, right? When AV streaming first became popular using Ethernet and networks as a technology, it began by leveraging the technology that was already created, which was IGMP or multicast routing. IGMP was designed to enable streams, though, to operate over the internet itself and allow the ability for someone to offer a video streaming service where they had to send one copy of the video stream to the internet as a whole. In this model, you could have effectively any number of listeners or consumers watching that stream send. And in this model, it kind of worked in the way cable TV infrastructure behaves, right? This is offering multiple channels of content. But in this scenario, you let the users select what channels they want to listen to, which comes with some drawbacks in a network model because this adds latency when switching channels or streams. Ultimately, IGMP, though, is the mechanism that lets users select the specific channels and control where the multicast streams go. And this is what the internet uses to support multicasting because now the multicast traffic doesn't go anywhere until it's explicitly asked for. So IGMP's importance here is that the internet would not be able to scale to the implementation we have today if we did not have this mechanism in place. And in that same breath, remember that the I in IGMP is for internet. So what we're talking about here is a layer 3 technology focused on routed infrastructure, not switched infrastructure. So what we have is designed for the internet, where latencies are highly variable, they're significantly longer, and what you see in a local area network or switched infrastructure with IGMP, it wasn't designed for local area network operation. And to get all of this back at layer 2, we need to rely on RFC 4541. This is covering IGMP snooping. IGMP snooping is a switch feature that's designed to reduce multicast flooding. This effectively prevents the switch from broadcasting everything coming into the switch to all of the nodes on the switch. And IGMP snooping also lets the switch listen to the IGMP join messages to build a map of what ports it actually wants to become members of within the multicast groups. So as we can see here, using IGMP snooping requires that one central device, either a switch or router, is going to periodically ask or query all of the end devices on the network to announce their multicast memberships. This central device plays the part of the IGMP querier, and it can be built into a switch or router. The IGMP query responses, known as IGMP reports, keep the switch updated with the current multicast group membership on a port-by-port basis. If the switch doesn't receive updated membership information in a timely fashion, it effectively will stop forwarding multicast to the delinquent ports where the end devices are located. Today, there are currently 3 versions of IGMP, with versions 2 and versions 3 being primarily used today, and each has its own benefits. IGMP 1 is really the basic level query response model, not used too much today. IGMP 2 added leave group messaging and group-specific queries, where IGMP version 3 introduced the concept of source-specific multicast capabilities. So now let's focus on a few slides here that show this IGMP snooping at play. So with the multicast switch, it'll forward a copy of the packet into each of the remaining network interfaces that are in the forwarding state. And this behavior works well for broadcast packets that are intended to be seen or processed by all connected nodes. In the case of multicast packets, this leads to less efficient use of network bandwidth, particularly when the packet is intended for only a small number of nodes on the switch. In this case here, the packets will be flooded into the network segments where no node has any interest in receiving the packets. What we see here, though, is that this issue actually multiplies even further when you add more transmitters to the switch. This ultimately creates more streams, and this doesn't scale, and it ultimately will lead to requirements of more provisioning for uplink bandwidth. It's also important to note that multicast is UDP-based, so its best effort delivery is not reliable. It can create congestion avoidance, creating slow start or TCP windowing adding congestion to the network. You can also achieve duplicate packets during transitions of the distribution trees that are created, and you can end up with out-of-order delivery, which also applies during the transition of destination trees. So the point of IGMP snooping is that it's designed to prevent hosts on a local network from receiving traffic for a multicast group that they have not explicitly joined. It provides switches the mechanism to prune that multicast traffic from links that do not contain a multicast listener or an IGMP client, and it's a layer 2 optimization for the layer 3 IGMP. IGMP snooping takes place internally on switches and is not a protocol feature. IGMP snooping allows a switch to only forward multicast traffic to the links that have solicited it. And as you can see from our previous example, the snooping is therefore especially useful for bandwidth intensive IP multicast applications like IP, video over IP, because it conserves the unnecessary traffic from flooding the network. In considerations of uplink bandwidth management with IGMP snooping by default, let's say you have a transmitter sending multicast streams to a bunch of different receivers with one transmitter that's fairly straightforward. But remember, IGMP is designed to be on a routed infrastructure with internet routers acting as control points for distributing the multicast traffic. Since there is no router in IGMP snooping, and that functionality of a control point gets delegated to the designated querier, which acts to fake out the systems that think they're talking to an IGMP router, when in fact they're actually talking to a switch. And the switch is what's enabling you to run the IGMP snooping. So one of the downsides to having the IGMP snooping in infrastructure is that my DQ has to see all the video streams network wide. And since I have a single control point, I have to send all of those different streams to the DQ, meaning I have to have an uplink that's going to be big enough to support all the streams simultaneously sending their traffic to that switch, regardless of whether any devices connected to that switch actually need it. So if I have a 3.7 gigabit stream, all is working well, but when I add a new 3.7 gigabit stream, I actually double the bandwidth to all of my uplinks. And if we add one more 3.7 gigabit stream, now I'm going to need 11.25 gigabits to get to my DQ, which is now exceeding that uplink available. So you have a couple options. You can increase the uplink, or you can architect the designated courier to a more optimal location in the network. So once you move that DQ down a level, what's actually going to happen here in this case is if I have to have the flexibility of having more transmitters and receivers all over my network, we're going to end up in a scenario of how do I move my DQ around while I build out my infrastructure? Well, the answer here is that if you have to configure each link to support all that traffic across the network, it's going to limit your scalability. And this becomes critical when you're dealing with things such as video, right? So remember, total network bandwidth actually is equal to your total transmitter bandwidth. So some final considerations here that we want to look at to pull it all together. Firstly, without a courier, your IGMP membership reporting will be incomplete, and the tables associating those member ports and multicast groups will potentially be incomplete, which means your snooping will not be working reliably. Some IGMP snooping implementations include full courier capability, and it's critical you only have one active courier per VLAN, primarily because you're sending these queries out as broadcast transmissions. So what tends to be an all too common pitfall comes from having multiple couriers on your network. So you do need to be mindful of that. Secondly, not going too deeply onto this topic, but the big picture here in multi-VLAN scenarios with routers is that you'll also need to provision PIM, the protocol independent multicast. PIM is then used between the local and remote multicast routers to direct your multicast traffic from hosts sending multicast to hosts that have registered through IGMP to receive them. There have been a few iterations, and the reigning champ of the router protocol wars that gets most commonly used today is PIM Smart Mode, which is RFC 4601. Lastly, maybe most importantly, IGMP snooping is actually not a standard. So you'll see the implementation of IGMP snooping handled differently depending on switch manufacturer's interpretation of RFC 4541. So taking all of that into consideration, let's look at some case studies here. And David, I'll throw it back to you.
Cool. Great, thanks, Frank. Yeah, so the following slides we're going to go through here are based on some common issues we see that are multicast related, as well as simply to provide everyone with a visual reference of what some of this looks like from both a software and network perspective. Right. So as we discussed previously, multicast frames are generally forwarded to all ports in the VLAN, unless IGMP snooping is enabled. In the case of IGMP, the switch is informed of the multicast group addresses and uses IGMP snooping to associate which ports are wanting to join those groups. These learned addresses are registered in the switch and used to ensure that only ports that have requested to join the multicast groups are sent those packets. However, there are many addresses, particularly in the local scope range of 224.0.0.0, that are not dynamically registered. Addresses in this range are generally broadcast to all ports on the VLAN, but depending on the switch manufacturer or switch configuration, these unregistered multicast addresses actually may be blocked or filtered. And now Tessera uses a set of addresses in this range for inter-device discovery. And here we see a list of the multicast addresses that are actually used by Tessera taken from the previous slide. We've got 224.0.0.251 through 224.0.0.254. So let's take a look at how filtering and forwarding of unregistered multicast traffic may impact Tessera communications in this case. So here on the left, we can see the system status window of an active Tessera system. And it's not very happy right now. We can see all of our devices are reporting faults. Unit 1 is reporting that it actually can't see units 2 and 3. We got Unit 2 reporting that it can't see units 1 and 3. And our Unit 3 is reporting faults that it can't see units 1 and 2. It's also acting as a proxy to our XLogic, so it reports faults that it cannot see the remote expander device. Essentially, nobody's able to communicate with anyone in this scenario. Now, if we turn our attention to the switch GUI, in this case, we've got a SG350 from Cisco. Our Tessera devices are connected to ports 1 through 4, and we could see that these ports are set to filter unregistered multicast. I've also got here a window from Wireshark, which is a common tool used to take network traces. And this window is currently showing us all of the IPv4 addresses seen at the 4 Tessera ports. If we look at the IPv4 address list listed here, we're actually missing 3 of those 4 IP multicast addresses that Tessera uses for discovery. So, I mean, the quick solution here is, we could set these ports to forward unregistered multicast. In this state, all unregistered multicast traffic, including our Tessera discovery traffic, is going to get forwarded to the ports this is enabled on. We'll now see all of the faults cleared in Tessera, and our remote expander device is now back in our device list as communications has been restored between the XLogic and its proxy. And now if we take a look at the list of IPv4 addresses that are sent to ports 1 through 4, we now see those addresses that Tessera uses, both for server-to-server communications at 224.0.0.252, server to remote expander communications, which is 224.0.0.253, and remote expander to server communications, which is 224.0.0.254. But what about a network where forwarding of unregistered multicast is not allowed and all ports are just set to filter? Right, in this scenario, IGMP snooping might be enabled and monitoring messages exchanged between hosts and the querier. Multicast traffic is forwarded to ports that have dynamically registered to join these IP multicast groups. So in order to allow our Tessera devices to communicate in this scenario, we need to statically register the needed addresses by adding them to the switch's IP multicast group address table. Once the addresses are added, they'll get assigned to the proper ports and traffic will be forwarded as needed. Now the procedure to statically register these addresses, it's going to vary depending on switch manufacturer. And again, here we're going to take a look at the GUI for the SG350. Now, initially looking at the IP multicast address table, we can see an address that's actually already been dynamically registered. This switch currently has both Tessera and Dante endpoints connected, and the 224.0.1.129 address, we actually brought this up previously in the presentation. What we see here, this is used for PTP clocking in Dante. So with all the ports set to filter unregistered multicast, our Tessera system, of course, is again in a state, is in a fault state. So let's start registering some of these addresses and see what happens. So in this case, we need to add all of our addresses manually. And again, this process may vary depending on the switch you're working with. We're gonna go ahead and start with 224.0.0.251. We specify the VLAN ID that our ports are connected to. We specify the multicast group address. Then we just click apply. And then looking above, we can see that that gets added to the IP multicast group address list. And we'll do this for each of our addresses up to 224.0.0.254. So we got 253. We've added 254 in the same manner. As each address is added, we can see that populate in the list above. And now we're at a point where we see all of our manually registered addresses in the IP multicast group list. But now we need to do one more step and actually assign these to the ports that our Tessera devices are connected to. So we'll go through, we'll statically assign these to ports 1 through 4. And as we step through this process, we're going to begin to see our system faults clear. So I've assigned 224.0.0.252 to ports 1 through 4. This is again our server-to-server discovery communications. And we see that all of the faults related to server class device communications is now cleared in Tessera. And I've gone ahead and done the same thing for 224.0.0.253. And here we see the last address, 224.0.0.254, being statically assigned to ports 1 through 4. These are used for server to remote expander and remote expander to server communications. And so once those addresses are assigned, we now see that the faults related to expander communications have cleared as well, and our system is completely fault-free. Now, we spent a little time there looking at all of this from the perspective of Tessera control communications. But a couple of our Tessera devices here are Dante capable. And similarly, scope multicast addresses are also used in Dante communications. So looking back to a previous slide, we could see the familiar address 224.0.0.251. It's also used by Tessera, as well as addresses 224.0.0.230, 231, 232, and 233. In this case, these are all used for like Dante-specific control, discovery, and communications. So in this case, we can also sort of use Dante controller software as a bit of a canary in a coal mine, right? A common scenario we see is that you open up Dante controller and you maybe see your devices, but you're missing pertinent maybe device information or clocking information. So if you ever launched software and you found yourself in this scenario, I suspect that multicast traffic is not being forwarded as needed. We know that unregistered multicast is being filtered on the switch we're working with here, and I had to manually register addresses to correct the Tessera communication faults. So let's look at doing the same thing for our Tessera Dante endpoints. So in lieu of time, I've gone ahead and I've added the multicast group addresses used by Dante as new entries to that same group address table in the switch. And now we just need to go through and assign these to the proper ports. So we'll look again here. And if we're looking at Dante controller in this scenario here, we could start off by seeing we actually have no information shown in this instance. So let's start by adding 224.0.0.251. We're going to add this to ports 5 and 6, as well as port 15. So those are two Dante endpoints, as well as the computer running Dante controller software. Now that that has been added statically to those ports, we can see our devices in Dante controller again, but we're still missing that critical device information, as well as our Grandmaster clock field is currently empty. And this is due to the fact that we still have additional multicast group addresses to add. The Grandmaster clock field, I might recommend, could be the first place that you look when launching Dante controller, as having no device listed there, or actually having multiple devices, could indicate a communications problem on the network. So as we work through statically assigning our addresses, we'll begin to see information properly displayed in Dante controller, and our devices should now be able to fully communicate. And as an example, here I've just assigned 224.0.0.231 to my Dante ports, and now we're seeing that, that clocking and device information populating within the software. So let's take a look at IGMP snooping in action from a Dante and network perspective. Right. So I've gone ahead and I've added a Dante multicast flow to the network, and I've routed it using Dante controller. This address is in the administratively scoped IP multicast address range, and it's actually dynamically added to the group address list as 239.255.70.244. And it also dynamically adds itself to the ports that our Dante endpoints are connected to. Again, these are ports 5 and 6. In this example, we're actually using IGMP version 2. And in IGMP version 2, you have your IGMP or your designated querier on the network, and this is going to send out general membership queries to 224.0.0.1, essentially saying, hey, who's out there and what are you interested in listening to? Host will respond to this with a membership report for the group or groups that they are interested in receiving traffic from. So IGMP version 2 also introduced the ability for hosts to indicate when they are, a little bit of goof there, bit of information I don't want to leave out here. So we see our membership report groups listed here, but actually what I did want to highlight first before we get into the leave message is we see our standard addresses there that we needed to manually register, the 224.0.0.251, 230, and 251. But of particular interest is now we also see that those two endpoints are sending out membership reports for 239, 255, 70, 244, which is our Dante multicast flow. So get back on track here. IGMP v2 introduced the ability for hosts to indicate actually when they're leaving a group or no longer wish to receive traffic from that multicast group. This is an efficiency improvement over version 1 of the protocol. An example of this might be simply unsubscribing our Dante multicast flow from the receiver. So here we see our Dante receiver. This is 169.254.119.179 on the network, and it sends out a leave message for this group. And this corresponded with me actually deselecting those channels or unsubscribing them from the Dante controller software. After sending this leave message out to the network, the querier comes behind and it sends out a group-specific query. Again, this is an efficiency improvement in version 2 of IGMP, and it's reacting to that leave message. So our Dante receiver indicated it wanted to leave that group, and as a response, the querier sends out, hey, does anyone else out there actually listening to this this multicast flow any longer. And once we see that group-specific query sent out, we'll see one last membership report come out, and that's from our remaining Dante endpoint that's on the network. So looking at this from the perspective of a device on the network that does not want to receive any of the multicast traffic from our previous examples, here just wanted to highlight, we've got two windows, both from Wireshark, showing the IPv4 addresses that are seen from the perspective of a random computer that's just sitting on that network. The image on the left shows this port after we have already enabled IGMP filtering unregistered multicasts. The image on the right shows prior to putting all these settings in place. And we can see here that additional traffic that this endpoint would typically not be interested in. On a small network, transmitting audio only, the difference here may be marginal, but you scale this up, you add high bandwidth video, and management of your multicast traffic becomes much more critical. So now that we spent some time on IP multicast and IGMP, let's take a look at some other protocols to manage multicast, specifically at layer 2.
All right, so the IEEE people, they're not stupid people in any stretch. They actually looked around and said, hey, this multicast thing's actually pretty cool, but we need to adapt it to work better in the layer 2 realm. So what they did was go back to their drawing boards, and they developed a bunch of technologies and rolled those up into the Ethernet standards organizations. And what this allows us to do is automatically let the network manage the multicast, right? So in this case, because it's IEEE, it's not IP multicast anymore, but it's layer 2 multicast. And what they developed was the AVB protocol. And this has the advantages with regards to automation, primarily using AVB. I don't have to do a lot of configuration or reconfigure my networks or consider over provisioning my uplinks to accommodate bandwidth restrictions. I still get to send one copy out to the network, but it goes exactly to where it needs to go. As you can see here, receivers that want to receive the network traffic will receive it, and anybody that's not interested does not receive it. And because all of this happens automatically from the network perspective, and the traffic only goes to the areas asking for it, not only the receivers are going to behave this way, but in this case, you'll also see that it'll only go from switch to switch when necessary as well, meaning I no longer have to worry about reconfiguring or over provisioning switch uplinks, which is another benefit. So one of the ways that this might look is that if I have an infrastructure that has several decoders to use as our previous example did, where we're providing streams that have 3.7 gigabits of information, I'll have one encoder and multiple decoders that are subscribing to that stream, and this will work great. I can add a second decoder to that same parameter, and if I have two different decoders that each want one of those streams, that'll also work without issues. I can then go ahead and add a third decoder, and depending on which devices are consuming that stream, if nobody's listening to that stream, then I don't have to over provision any of the network to coordinate for this. Because there are no listeners in this model, I don't have to overdo my uplinks. And as a result, my bandwidth needs are restricted to the number of unique receivers on the network rather than the number of video streams or transmitters deployed on the network. It's also important to note that with AVB, you are leveraging the protocol MSRP, which is reserving and managing your bandwidth, right? So the multiple streams registration protocol provides bandwidth management and access control on each media link. When an AVB listener requests an audio and video stream from an AVB talker, the MSRP reserves that required end-to-end bandwidth after first checking its availability. And because MSRP is going to put a cap on how much bandwidth AVB is permitted to reserve, MSRP protects your non-media traffic just as it protects your audio and video traffic. And as it turns out, that IEEE also came up with a better way to manage your VLANs, right? So you can also take advantage of the automation with respect to VLAN configuration. So now what happens is when a media streamer or AVB capable device is connected to an AVB port on your switch, they're going to come online and say, hey, I'm about to stream some media here, and those ports on the switch can take the talkers and listeners and place those into their own AV VLAN automatically. This is going to let the network isolate that traffic automatically for you. And what this provides you is that it removes the administrators from the configuration altogether, right? So if the IT admin goes into your network room and unplugs a port and goes and plugs it into the wrong port, nothing bad's going to happen. All is well, and it's going to look at that and say, hey, this is a stream, and I'm going to put it back in the right VLAN and reconfigure it for you automatically. Simultaneously, non-media streaming devices will be in a different VLAN, and you will have the automatic partitioning again. So nothing has to be done from an administrative overhead perspective, thanks to MVRP. Additionally, you end up with a scenario using AVB that gives you end-to-end latency management as well, right? So you get bounded latency, precision timing, and synchronization through the network, which gains you the consistent performance across the network. And this is using the IEEE 8021AS protocol, known as Generalized Precision Time Protocol, or GPTP, and this sits at the heart of your time-aware AVB network. And in this case, every link will be checked and synchronized individually, ultimately improving accuracy, synchronization, time, and robustness when compared to other protocols. Standing on top of this, the IEEE also rolled in forwarding and queuing for time-sensitive streams, FQTSS, and this applies QoS and traffic shaping to your AVB traffic by releasing AVB packets in guaranteed slots. They arrive in timed intervals. So AVB traffic flow is both reliable and smooth when going across large AV networks. This traffic shaping not only benefits your AVB traffic, it also affects media traffic delays that would affect your non-media bandwidth, right? So everything on both sides of your network are going to be improved due to the FQTSS.
Okay, and putting this all together, what this means is that there are a category of switching hardware called enterprise-grade switches, and these are switches where you're going to have significant capacities underneath the hood, right? Additionally, when utilizing AVB Layer 2 multicast solutions, you'll want enterprise-grade switches that are AVNU certified, which means that they've gone through interop testing, guaranteeing that AVB from other AVNU certified vendors will operate without issues. Shown here, we have couple major players, Cisco and Extreme, that both have options here when working with Biamp, Tessera, and Tessera Lux. In general, the main benefits of enterprise-grade switches come in things like switch capacity in terms of bandwidth, packets per second, and processing power. Additionally, these types of switches have features like redundant power supplies. They're designed to operate 24/7 under full load, meaning these run fully not just with the kind of random bursty normal everyday traffic, but as well with AV traffic, which is very consistent in level packets that are utilized. If you're working with any sort of large bandwidth video over IP networks, Layer 2, Layer 3 multicast audio solutions, or placing any AV network gear on a customer's network, picking the right tools and getting ready to have conversations regarding the switches that are used is important, as well as spending the time to work out any issues that might come up. However, maybe another route you can consider here is that not all systems require the complexity of putting IP multicast or AVB multicast onto managed enterprise-grade switches. In cases where you're not deploying distributed video systems with high resolutions and your focus is maybe smaller individual conferencing spaces, you might consider taking the path of least resistance here and connect your Biamp audio conferencing systems together using Tessera Connect. Leveraging sort of these high bandwidth demands onto other infrastructures. Tessera Connect is plug and play, provides PoE Plus and all the automation benefits of AVB without having to do sort of any of the configuration of an enterprise-grade managed switch, and allows you sort of seamless integration with the rest of the Biamp Tessera devices, potentially making the entire installation a full category cable solution as well. Just showing an example of this, as you can see here, even just using a simple interface like this Tessera Connect, this could scale up pretty quickly and effectively. Here we have 2 Tessera Connects, so you could daisy chain up to 4 of these, giving you a total of 13 AVB connected devices. But in this scenario, you have the ability to cover multiple rooms with Tessera amplifiers, Tessera speakers, USB and/or Bluetooth audio, and pilot microphones effectively, all without having to do any sort of switch configuration or management in this case. So that kind of brings us to the end of the presentation.
Yeah, I would just add, a lot of the technologies with networking, Cisco in general, or most switch vendors have their own training and certifications, so do consider going out and finding resources from the manufacturers, as well. Biamp has its training. None of these things actually are something that without having experience going through it, or, try and build a network of network people that you can build upon their knowledge base and learn things yourself. So, this is a collaborative effort whether you're doing it all yourself or working with your IT folks, with your customers. So just prepare to get as much knowledge as you can so that you can communicate to the people that you're working with what your requirements are.
I want to thank everyone for spending some time with us today. Hopefully you found some of this information useful and helpful when you're on site there, potentially dealing with some multicast related issues, or talking with a customer of yours in regards to adding devices to their networks that take advantage of some of these multicast group addresses that we went over today.
Yeah, and if you have any further questions that you think of going forward, just shoot them through to support@biamp.com, and we'll take a look to get those answered for you as well. Thanks, everyone.
Okay, yeah, thank you.